So it's a good time to start. So let me just share my screen. I hope the screen is visible and my voice is clear. So as discussed in the last uh, session, we are supposed to solve assignment number 3 in this session, and maybe if time permits, then we will also see assignment number 4. So uh, I I won't be revising the lecture notes now because it takes a significant amount of time. Rather than I will be just giving a brief idea of whatever topics being covered in the lecture uh, whenever it's needed. So yeah, I hope it's clear. Any uh, comments on that?
Hello. Yes.
Yes,
Yes, sir.
yes, Vivek. You want to say something? Yes.
Yes, sir.
Okay. Yeah. Let's begin then. It's, uh, hmm, 6. Introduction. Yes. 5th March. Okay. So we will discuss assignment 3 and 4. So let me just paste question number 1 here. Let's go. Yes. Here it is. It says which of the following are algebraic extensions. So you have Ri over Q, you have R over Q, and C over R, and the last one is Q C1, Q of Xi1, Xi2, Xi3, and so on. Where Xin is the nth root of unity.
Sir,
Yes.
algebraic extension, that means
Your
satisfies.
voice is breaking. So algebraic extension means each element of that the extended field is algebraic over the base field. That means each element satisfies a polynomial over the base field.
Okay, okay, sir.
That we have seen in the very first lecture. Yes. So and also we have seen that each finite extension is a algebraic extension. So
Yes, sir.
solution 1. So in the case of Qi, so you know that Qi over Q is an extension of degree 2, right? Right. So this implies qi of q is a finite extension and thus a algebraic extension, because every finite extension is an algebraic extension. That's a theorem that we have already seen. So first one is an algebraic extension by using the finiteness of this extension. Okay. Now the second one is R over Q. So what's your input over this R over Q, whether it's a finite extension or not? And if it is not finite, can it still be a algebraic extension or not?
R over Q. Sir, first of all, no
Sorry,
extension.
R over Q.
I think it is not an algebraic extension.
Why?
Reason is that because R haven't any polynomial.
R polynomial means there can be polynomials in R. What's the problem? It says each element
So we
of
can say
R
it is not a finite extension. Simply we can say
still can be infinite. An infinite extension can also be algebraic. It's just a necessary condition. Sorry, it's just a sufficient condition, but
sufficient.
but not the necessary one. Without finiteness also the extension can be algebraic, and we will see such an example soon. What else? We have already seen this thing in one of the lecture. Just a revision of that part. Just a collection of old facts so far. What about pi?
Pi is irrational number.
Irrational number, and whether it's algebraic or transcendental,
It is transcendental.
so it's not algebraic, right?
Yeah.
So pi belongs to R, and pi. So by algebraic number, we mean any complex number that is algebraic over Q. So R is a subfield of Q, so a subfield of C. So pi is not algebraic as a number belonging to C. That means pi is also not algebraic as an element of R also, right? It's the same thing, that it doesn't satisfy any polynomial over Q. So pi belongs to R, and pi is uh, is not algebraic over Q. Thus, it is not an algebraic extension. Okay. What about the third one? That is C over R
It's satisfied.
satisfies.
Any complex number is algebraic over R.
Okay. The reason?
Reason because C over R is 2.
The degree is 2, right?
Yeah.
So C over
Finite
R is
extension.
nothing but R adjoint with I, right? This is what this is. A plus eta B such that uh, A and B are inside R, right? Because it's a degree 2 extension. I satisfies x square plus 1 over R, and I is not inside R. So it's a degree 2 extension, and any degree 2 extension will be of this form: A plus that adjoint number times B. A and B are inside the field, right? So uh, this implies R over I, that is C, is a degree 2 extension of R, which implies uh, it is a which which implies C over R is an algebraic extension. Clear? Okay. What about the D option? That is Q of xi1, xi2, so on over Q.
It's again finite extension.
Finite extension. So it's not stopping at any point. Certainly not finite. For any n, you
Okay,
have
okay. Zeta n is given only. For zeta, any zeta n,
it's for any zeta n it is finite, but here the number of zeta n is not fixed. It's increasing. At each step you are adjoining one zeta.
but sir, it is a collection of natural numbers, na? Zeta n 1, 2, 3, 4, 5.
It's countable, you can say, but,
Yeah.
but it's infinite, right? Countable thing is also infinite. Then what? So first of all, see that this is an infinite extension because for each n belongs to n, there exists P, which is a prime. There exists, say, prime P greater than n. There's a prime P greater than n, and this and Q adjoined with that xi P over Q. So this we have seen, right? When it's a prime, then the degree over Q is P minus 1, right? Because it satisfies xp minus 1, and then you can take the x minus 1 factor outside, and it is 1 plus x plus so on to x raised to p minus 1. And using Einstein criteria, we prove that that polynomial is irreducible. So its degree is p minus 1 for any prime p. Okay, so this is an infinite extension because for each n belongs to n, there are just a prime p greater than n such that this is the case, and which implies that uh, q of xi1, xi2 dot 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 uh, so on. So this over q is nothing but q of xi1 dot 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 xi p minus 1 and xi p plus 1, and then dot 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 over so this is over q of xi p. Just a minute. So what I'm doing, I'm just trying to tell you that how this extension is infinite. Although this has nothing to do with the solution of the question, because uh, we won't get that it's algebraic or not once it is infinite, but it may be useful in some other context. So it's good to know that this is an infinite extension. Okay, so this is, and then you have q xi p over q, right? So this is what? This is p minus 1 times uh, q of xi1 xi p minus 1 xi of p plus 1 over q of xi p, right? So this is something greater than equal to 1, right? Here again the infinite thing will go on. This extension we don't know whatever its degree, but certainly this is p minus 1, and which implies this initial extension, this is always greater than equal to, although it would never be there, this is greater than equal to p minus 1, right? Clear? In fact, yeah, in fact what we can do, we can simplify it more. For each prime, we can just put for each prime p. So let me just change the approach a bit. So for each prime p, we have p belongs to n, we have q is ip over q is p minus 1, and then we break it like that. So this extension has is greater than equal to p minus 1 for each prime, right? And for each number n, you have a prime greater than n, and this implies that this is infinity, right? You get it? Why? Because if it is finite, say its degree is n, then you can find a prime greater than equal to n plus 1, and then this condition will violate. You can find prime greater than any number, right? So that's why it's never going to be a finite number, because once it is finite, you can find a prime which is greater than that number, and this condition is violated. So it's going to be an infinite extension.
Okay,
Clear?
sir.
Okay. But uh, each zeta I satisfies.
That means, sir, it is algebraic extension or not?
So that
Okay.
doesn't tells you anything. Once it is infinite, you have to check that each element satisfies a polynomial. If it is finite, then each finite is algebraic, so the story is over. But if it is infinite, you can't use that infinite thing to check whether it's algebraic or not. You have to go by the definition that each element satisfies a polynomial. Okay, so that's what we are doing here.
Okay.
Okay, so although this is infinite, but each zeta I satisfies xi minus 1 over q, right? By definition, it is the ith root of unity. Okay, so it satisfies this. Thus, this implies each zeta I is algebraic over Q, and thus this extension is an algebraic extension, because this extension is the smallest extension containing these zeta is and Q, and each element of Q is algebraic and each zeta is algebraic. So this extension is also an algebraic extension. Is an algebraic extension. So that's the example I was talking about. So this is an example of a of finite and infinite algebraic extension. So algebraic extension need not be finite always. This is an example of an infinite algebraic extension. Or I can simply say that this is an infinite algebraic extension. That's it. So that's why when you are saying that it is infinite, so we can conclude it is algebraic. I told you that no, it is not always being the case. One side is true, but the other is not. Okay. Okay. So
Yeah, okay, sir.
got it. Now maybe we can move to the second question now. And advance it a bit. It says let E, L, and K, let L and K be uh, algebraic extensions of the field, and E be an extension of L of K. Define Lk to be the subfield E generated by elements of L and K. Then Lk is an algebraic extension of F. So let me brief you the story here. So you have fields L and K, which are algebraic extensions of the field F. You have F in the bottom. Then you have L and K as two algebraic extensions. So here it is K, say, and here it is L. So this is an algebraic extension, and this is an algebraic extension. And then you have Lk, which is being generated by elements of L and K.
Sir, LK, that means extension field containing union of the elements, na L and K.
So union might not be a field. So it's a
Intersection is the field. Oh,
no, but intersection won't be the containing the all the elements of L and K, na? So it's the field generated by L and K. What it is mean by smallest field containing L and K. Okay, the smallest one that contains Lk, and then Lk is a subfield of E. So that is the tower. So you have L and K to be algebraic extension of F, and then E be an extension of L and K. So here E and is an extension of L and K, and Lk is a subfield of E generated by the elements of L and K. Okay, so then the question is whether Lk is an algebraic extension of F. Okay, so Lk contains Lk is generated by elements of L and K, right? Also, each element of L and K are algebraic over F. Thus, Lk is generated by algebraic elements generated by elements that are algebraic over F, right? Yeah. So its generators are algebraic, and this implies Lk is an algebraic extension. I will tell you why. Lj is an algebraic extension of F. Since if A and B belongs to Lk are algebraic, then their sum, their difference, their product, inverse product, all these things are algebraic over F. Are algebraic over F. Then there's some difference product and product times and the inverse product that is also algebraic. Thus, uh, if the generators are algebraic, then the field generated by those generators will also be algebraic, because how will you generate the field? You will just take their products, multiplication, and the inverse or their inverse product, anything. So anything you can take, and then they will be give you the algebraic extension. So that's why Lk is algebraic over Lk is an algebraic extension of F. Okay. This is what we were supposed to check in question number 2. Now let's move to question number 3. I won't solve this question completely. Rather than I will just give you some hint, because it's just based on this question, and you just need to play with some numbers, and that's it. So it says L and K be algebraic extensions of F, and E be an extension of L and K. Let Lk be as defined above. Then what is L intersection K? What is the degree of L intersection K over F? So, so see, L intersection K is contained in L, and L intersection K is contained in K also. And since F is contained in L and K, we have uh, F is contained inside L intersection K, because it's contained in both, so it will be contained in their intersection. So there is a slight modification in the tower that we formed. So till here, everything will be same. Let me try to copy it as it is if I could do. See. Yeah. Yes. So till here, everything is same, except that so here we have the same tower like this, but uh, between F, L and K, we have L intersection K also. So I just mean to say that will be L intersection K. The algebraic thing will also follow because each element of K and L is algebraic over F. So it will be algebraic over L intersection K as well because it satisfies some polynomial over F. That means, and F is inside L intersection K, so it will by default satisfy polynomial over L intersection K. And L intersection K will also be algebraic over F because L and K both are algebraic over F. This is the situation that we have. And in addition to that, it is given that uh, it is given that LK over F is LF KF. So LK over F is equal to the degree of L over F and degree of K over F. So LK over F, that part is same as L over F and times K over F. So from the diagram of the above tower of fields, LK over F is what? This is LK over L and L over F. And also this is same as LK over K and K over. So you compare these three equations, LK over F is same. So LF, this is same. That means KF is equal to LKL. This implies KF is equal to LKL. And here you have KF. This will cancel out. LF is equal to LKK. LF is equal to LKK. So you get two new equations, right? Now use these things. Use these conclude that the we were supposed to find L intersection K over F, right? We will end up calculating that L intersection K over F has degree. So you use these equations and the tower nicely to finally conclude this, and that is doable. You just need to play with these numbers and these towers. This is the main equality that one has to think of, and then it is doable. Okay, so we will move to the next question. It says, which of the finite fields are not algebraically closed? So for that, one has to see the sample problem number 3. So from sample problem. So it was a problem discussed in the lecture videos. Discussed in lecture videos. um, it is evident that no finite field is algebraically closed. So that questions that sample problem tells you that each finite field is not algebraically closed, and in fact you have f uh, p closer its degree over ft to be infinite. It is not a finite extension, it's an infinite uh, extension, and that is not just for p but for any p raised to n you can take. Okay, so now this implies that these are not algebraic closed. In fact, their algebraic closure is of infinite degree over uh, the base field. So all options are correct. All of them are not algebraically. Let me just put my charger on. It's clear, Vivek. Have you seen that sample problem?
Sir,
Yes.
it's like it's clear. Like, uh, can you say any example that not satisfied F2 or F5 or F7?
So the idea in the sample problem is, so for any p, fp closure contains fields which are having p raised to n uh, degree. So what I mean to say that so that was for any prime p. So in that
Means only for
example,
prime numbers.
yes, but see, ultimately it will give you for p raised to n also. So and any field is of the form p raised has cardinality p raised to n. So that example basically what it does, it for any p, it says that fp closure contains subfields of order p raised to n for each n belongs to n, right? So since it contains subfields of order p raised to n, maybe I can tell you what exactly the uh, sample problem was. I will just speak it and then. So it says FP closure contains a unique subfield of order p raised to n for each n greater than equal to 1. Okay, so in fact, we don't need the uniqueness here. So contains
Okay.
subfields of order p raised to n for
For
each
every
n
n.
belongs to n. And this implies that FP closure uh, have over FP uh, is of infinite degree, right?
Greater than.
because
p
it is greater.
minus 1.
Yeah, it is. You can say that it is greater than equal to n for all n belongs to n, and then it will imply that it is of infinite degree, right?
Okay.
For
Right,
all
sir. Okay.
n belongs to n, and then it will imply that fp closure over fp is equal to infinity. And in fact, you don't need to from here only you can say that even if it's a prime power, say p raised to r, then also this will hold, because
Okay,
the
sir.
closure of fp contains each subfield of order p raised to n. So closure of fpr has to be greater than the closure of fp, because fp is contained inside fpr, right?
Yes, sure, sir.
So, and so for that closure also, it will hold that it contains subfields of all pth powers, and then uh, there also you can say the closure is of infinite dimension. Okay, so this certainly implies that fp closure is not same as fp. Okay, and here all these are prime numbers, so for all of them, they are not algebraically closed. So all
Yes.
options are correct. Okay. Oh, so clear now, Vivek?
Yes, sir. Done.
Okay. So I will then copy paste another question. It says which of the following statements are equivalent to the other three. First one is uh, K is algebraically closed. There are no non-trivial extensions of K. Every irreducible fx belongs to kx has distinct roots in K. So let me just see one by one. First one is K is algebraically closed. There are no finite non-trivial extensions of K. So we are checking. So I will give them numbering, say A, B, C, and D. So A, if and only if B will hold. Why? Because if K is, say, not algebraically closed, then there exists a there exists something inside K. There exists alpha belongs to K, such that alpha is not algebraic over K, right? And uh, this implies, okay, then if E alpha be the uh, be extension, so it is not algebraically closed, means there exists a polynomial, sorry, not just not alpha. Algebraically closed means if all of its polynomial have roots inside uh, the field, right? So there exists uh, ft belongs to k of t, such that ft has no roots in k, right? There should be a polynomial which does not have a root, because algebraically closed mean it for all polynomial there exists a root, and this is equivalent of saying that for all polynomial there exist all roots, right? That we see the equivalence of both the statement. For all polynomials, it happens that it has a root. Then for all polynomial, it will happen that it has all roots. So similarly, if for a polynomial there is a single root missing, means there would be a polynomial for which all roots are missing. Okay, so there are just ft such that it has no roots in k, and uh, so let e be the splitting field of f, be the splitting splitting field of ft, right? uh, then we know that the degree of splitting field over the base field is less than equal to the degree of the polynomial factor, factorial, right? So this is of course less than infinity, and e is not same as k because it doesn't contain a root, right? So it cannot be the same. This implies uh, it is strictly greater than 1, the dimension, and it is less than infinity. So why we need greater than 1? Because we want non-trivial extension, right? So this implies e is a finite non-trivial extension of k. So we assume that if k is not algebraically closed, then there is a finite non-trivial extension of k. So not a implies not b, or this is same as b implies a. That you know, right? If a is not holding, then b will not hold. That is equivalent to say that b implies a. That is just
Sir, the
reverse.
second line is and E naught is equal to K. This implies that part. Can you try to clear it?
So E not equal to K means this degree is greater than 1, right? Because if it is 1, then E is same as K.
So E over K is less than is equal to infinite.
Oh, not less than, this is strictly less than infinite. This is less than infinite. That part we have already concluded here, that E over K is less than infinite. That will come here. This is just for 1 less than E over K, the degree of E over K. Okay.
Okay, sir. Right.
Okay. Now let's see. Not B implies not A. So now mm, let if so B says that it has no non-trivial finite extension. So now let uh, L be a non-trivial finite extension of K, right? So it's a non-trivial finite extension of K means L is not equal to K due to non-trivial part, and it is finite. That means L over K is an algebraic extension of K. Finite means algebraic, which means the existent extension, all of its elements satisfies the polynomial in K, but K is supposed to be algebraically closed. So all polynomials in K has roots inside K, right? So how its roots can go outside K if it is algebraically closed? So this contradicts that K is algebraically closed. because algebraically closed means it has roots for all of its polynomial inside uh, itself. But it is saying that there exists a non-trivial extension such that all elements of L satisfies a polynomial over K. So that cannot happen, right? Because L not equal to K, what does this mean? There exists some alpha inside L which is not inside K, and that alpha is also satisfying a polynomial inside K. So that means that particular polynomial is not having roots inside the field K. Its roots are lying outside K, that is inside L. So that is contradiction to the algebraic closeness of K. So this contradicts that K is algebraically closed, and hence this implies uh, not A B same as not, or maybe this I can say this implies K is not algebraically closed, right? This implies because if it is algebraically closed, then its roots cannot lie outside it. So this implies K is not algebraically closed. Vivek, that is clear? It's
Yes, sir. Fine.
because if it is algebraically closed, then all of its roots should all of its polynomial must have roots inside it, but it is having an non-trivial extension. That is an algebraic extension, so it cannot be algebraically closed. So not B implies not A, or A implies B. So A is same as B, that is clear. Now C, every irreducible fx belongs to kx has distinct roots in K. So distinct root is not guaranteed. So C is not same as, so now we will see. So we have already seen that A is same as B. So now we will see A does not implies C, and it is very easy to see. There is nothing we have to do. So uh, fx equal to, say, x minus 1 square belongs to kx, right? And it has repeated roots. So even if it is algebraically closed, it doesn't guarantee that it has all distinct roots in K. So for example, if you want to take an algebraically closed field, you can take it to be Cx, but this is, so C is algebraically closed, but and x minus 1 square inside Cx, and it has repeated two roots. So it's not guaranteed that each polynomial will have distinct roots, right? So they are not equivalent. Now the D part. So that we will make equivalent with the part A. So it says if L is a field extension of K, then K equal to A belongs to L. A is algebraic over K. So that's what we discussed while proving B is same as A. So now we will show D is same as A. So it says L is a field extension of K, then K is A belongs to L such that A is algebraic over K. So this means that So this is for all for any extension, right? L was any extension if L is a field extension of K. So this is saying for any field extension L of K, this holds. We have K to be same as this. So this implies there does not exist uh, a field extension of K which contains an element outside K that is algebraic over K, right? So there does not exist a field extension of K which contains an element outside K uh, uh, that contains an element, say alpha. I will say alpha outside a K, and such that alpha is algebraic over K. So this implies that all polynomials in K has roots in K only, right? Because it doesn't contain roots outside K. It has all the roots inside K itself. So which implies K is algebraically closed. And or you can see all these things are if and only if K is algebraically closed, if and only if all polynomials in K has roots in K only, and if and only if there does not exist a field extension of K which contains an element outside K such that alpha is algebraic over K, because if it happens, then it won't be algebraically closed. And that is also if and only if to this statement that for any field extension L of K, we have K to be this. So D is same as A. So thus A is same as B, and that is same as D. Clear? Any doubt?
No, sir, it's complete.
Okay.
A implies B implies D. And sir, where was the statement third?
So third
Every
was uh, this. It says every irreducible fx belongs to kx has distinct roots in k. So we took it like
oh, that
reducible.
means because this statement is different.
Yes. And
Yep.
we actually took the wrong example. Thank you for that. So we took here that fx equal to x minus 1 square belongs to cx, and it has repeated roots. So in the earlier part it was saying every irreducible fx belongs to kx has distinct roots in k. So first of all, this thing doesn't make sense, na? Irreducible one, because
Okay. Every
if k is algebraically closed, then each polynomial is reducible. Only irreducible polynomials are the linear factors, because each polynomial you can reduce.
every irreducible has distinct roots. Then sir,
So see,
yeah.
I just gave a wrong example. Let me just correct it. So means a if K is uh, algebraically closed, then each polynomial in K splits into linear factors, right? Because it is irreducible, so because it's algebraic closed, so it contains all the roots, so it must split into linear factors,
Factor.
right? And
Okay.
that that means the irreducible polynomials are the irreducible
Every irreducible polynomial has.
polynomials in K are just linear polynomials, right? Clear? There can't be anything else, because if it is a polynomial degree greater than 1, then you can split it and then it will become reducible. Clear?
Okay.
And which has which have only which have only a single root in K. Right? It is linear, so it will be satisfied by only one root, and that's why the is violated. It says it contains distinct roots. So if it is only one, then how the question of roots will come into one picture? K is algebraically closed, and each polynomial in K splits into linear factors. The irreducible polynomial in K are just the linear polynomials, and which have only a single root in K. Thus, they don't thus they don't have distinct. So they just have one root in K, right? So they cannot have more than one root. So they don't have distinct roots. Okay. Clear, Vivek? Thanks for this query. Actually, I didn't notice this irreducible part. Irreducible part guarantees that uh, you cannot take the polynomial that we were taking earlier. But still, the conclusion is same. A is not same as C. Okay.
Okay, sir.
Now let us move to the next question. The algebraic closure of Q is countable. So that we have already seen in one of the lecture notes. So C contains the algebraic closure of Q, because C is algebraic closed and Q is contained in C. So algebraic closure of Q will be contained inside C. You cannot cross algebraically closed field, right? So uh, we have already seen we have already seen that mm, the number of, I should say, the cardinality of Multi of uh, algebraic quantity of complex numbers that are algebraic over Q is countable, right? That we have seen in the first class where we were discussing the algebraic and this thing, transcendental numbers, right? There we see to prove that transcendental numbers are uncountable, we show that it is uh, okay. So, and this is just a so, something more than just Q closure. Okay, so which implies that Q closure is countable. So yeah, let me just move to the next question. Next question says algebraic closure of a finite field is trivial, finite, uncountable, countable or uncountable. So this option is not true. Uh, which question was there? I think in one of the question we have discussed this now, where the sample problem number 3 was coming. Question number 4. So this is from question number 4, and this won't happen because similar uh, to the case of uh, Q and Q closure, one can show that uh, the closure of any field has uh, countable degree over that field. Or one can show that closure of any field has countable degree over that field. So in while proving that Q closure is countable, what we do, we argue that the number of roots of polynomials in Q are countable because each polynomial has a finite degree, and for each fixed n, the number of polynomials of degree less than equal to n is finite. So you can see that argument. So that means you can have only countable many roots of polynomials inside that particular field, and thus the closure has a countable degree over any field. Okay, for any field it will hold that f closure will be of finite degree over f. Oh, sorry, countable degree of f. It may be equal to f if f is algebraically closed. If f is not algebraically closed, then it at max has countable degree. Has at max countable degree. At max, I should say because similar to the case of Q and Q closure, one can show that closure of any field has at max countable degree over that field. And mm, since FP is fine, thus uh, FQ closure is countable for any finite field FQ. So Q is some, you can say, power of P. So because it has countable degree over FQ, and we have seen that if K is a extension of F, then what is the cardinality of K? It is just cardinality of F raised to the power of the degree of K over F. So here the degree is countable, and the base field is of finite cardinality. So some finite number raised to the countable number is again a countable thing. So thus FQ is countable for any uh, finite field FQ. Okay. Uncountable part will be vanish. Okay. So let me go to the question number 8. Is it clear? Huh? Eighth question. Sorry, seventh one.
No, sir, clear. Fine.
Okay. So now eighth question says, now I guess the easy questions will come. So it says, let S be the statement that every polynomial Px and Qx in Fx that do not have a common root are relatively prime, then S implies F is algebraically closed. So it says that if two polynomials don't have a common root, then they are relatively prime. So generally, relatively prime. So in general, Px and Qx belongs to Fx are said to be relatively prime relatively prime if they don't have a non-trivial common factor, or in other words, their GCD is just one, right? But here it is saying, so statement S is saying that they are relatively prime if they don't have a common root, means their GCD splits into uh, uh, what to say, linear factors. And so you can determine whether two polynomials are relatively prime or not by just looking at their roots. And when you can do that, when the polynomial splits into linear factors, right? So S implies that each polynomial in Fx splits into linear factors, and thus this implies that F is algebraically closed. So this is a true statement. So these questions are just you think of the definition for a moment, and then they will just follow. So let me move to the next question. I want to finish assignment 4 also today, if possible. So it says Uh, Ninth question says is fx belongs to qx be an irreducible polynomial of degree d and k denotes its splitting field. Which of the following statements are true? So first is already done in the class, right? This is being discussed in class, that the degree of the splitting field is always less than equal to the factorial of the degree of the polynomial. So this is discussed in lecture notes. K subset of R. So is it true or not? This is not true because for fx equal to
Sir,
x square plus
K
yes,
is a splitting field. Okay.
yes.
So any example of suppose if you take x square plus 1,
Mhm.
then plus minus I, and
Which is q adjoint I, right?
yes.
And that is not inside R because I is not inside R, na? So for which the second part you are asking example.
Yes, sir.
So this is the example, right? So the you take any polynomial whose roots lie outside R, then if that is if it is in a splitting field, then it must contain that root, and that root is not inside R. That means that field itself is not subset of R. That's what I did for x square plus one. We know that it root will lie outside R. Similarly, if you take the third root of unity zeta 3, then it is it satisfies xq
Also
minus
outside
1,
of R.
but it is outside of R. Zeta 3 is a complex number, right? So yeah.
Okay, sir.
So you can take any polynomial which contains a complex root. That will do your job. You can construct this polynomial of your own also. You take a complex root, complex number, and then x minus that complex. So say the complex number is z, then x minus z and x minus z bar. So this will give you a polynomial in reals. You just make sure that it is in rational also, and then it roots is z and z bar, which are not real numbers, and their splitting field will not be inside R. This is a general example you can consider. Okay.
Okay, sir.
Okay. So K is so this is also done in the class, right? So if Q is a so you adjoint with Q all complex roots of fx. So all roots of fx lie in C only, thus it will hold. You adjoint this Q with all the roots, and then it will be the splitting field. Now the fourth one is not true. Yes, Vivek, you are saying something?
Sir,
Hmm.
uh, a statement is let fx be an irreducible polynomial of degree d only.
Hmm.
Okay, na? So can we say q over q is less than is equal to factorial d? This statement.
So this is always true, na? This is uh, already discussed in the lecture that for any polynomial, not even reducible, of degree d, it's
But here fx is irreducible of degree d, na? Only fx. This is the
yeah, but
condition, I think.
But even if you remove this irreducible one, then also it is true that you consider any polynomial in Qx, or in fact not in Qx, you consider any polynomial in any fx, capital F of x, any field. And if K is a splitting field, then the degree of K over F is less than equal to D factorial. This is
It
for
is
any,
universal true. It's right.
so for irreducible also it is true, na? What's the problem? It's just a sub case of it. Which, I hope that's what you want to ask or something else.
Sir, I am little confused in the irreducible
So
of degree.
you remove that irreducible condition. You just consider you just remember what we discussed in the uh, last lecture. I think we revised that, or if not, it is already there in the lecture notes, that you
Fine.
consider any field f. You take a polynomial in this in the fx. Then if k is a splitting field of that polynomial, then k over f has degree less than equal to the degree of the polynomial. So that is for any polynomial, irreducible, reducible, any polynomial. So if it is for any polynomial, it will be true for irreducible also, na?
And the second part is which of the following are not true, necessarily true.
The second part,
In the question, which of the following are not necessarily true?
huh? Yes. So the first part is okay.
Yeah,
Okay,
first is okay.
okay. I am maybe writing
Well, then,
in the opposite direction. So these are not necessarily true. So this is true. So you want me to cancel this,
yes,
and this is not true. So this should be correct. And uh, k. So this is also true.
yes.
So
So this is
this
cancelled.
should be, this is cancelled, and this is not true. That we will see. So you want me to do this?
Yes,
Okay. Thank you. Yeah. So for this, what we can simply consider. So consider uh, xp minus 1, right? So it has splitting field. Its splitting field is what? Just use adjoint in splitting field is q adjoint with zeta of p, right? I should write it little bit. So consider x square xp minus 1 belongs to qx. Then its splitting field is q zeta p, and q uh, zeta p over q has degree p minus 1 that we have already seen, which is less than the degree of xp minus 1. So it is not necessarily true that the degree of the field is same as the degree of the polynomial. It may be less than or even more than that. Okay. Okay, so with that, I think we can move to the next question. That says, it says let k be qi for each of the following polynomials. Fx belongs to kx. It's called, yes. Yeah, k equal to qi for each of the following polynomial. F belongs to qx, Is K the splitting field? So this is the field, and for this polynomial, we wanted to see that whether this is a splitting field. So first one is not there because it has -3 as a root. Sorry, I should write that root of roots of fx is only -3 is a root of f, and -3 belongs to q, right? So its splitting field is just q only, not qi, right? Splitting will be the smallest field containing all the roots. So it is just q, not qi. Now x square plus 3. What's your take on that? So
It is
f
also
has,
not
yes, f has roots mm, plus
uh,
minus.
minus root 3i.
So this is, it will go here minus, you know, so plus minus root 3i,
I.
right? And it is not inside,
K.
does not belong inside k. So the first case, in the first case the field was smaller than the k, and in the second case the roots are not inside k, so it will not also not be there. Fx equal to x square plus 2x square plus 1. So this is same as if you see x square plus 1 whole square. This is correct because it has roots, repeated roots, I,
Plus minus
I,
I.
minus I, and minus I. Four roots are there, and all of them are inside k. And what about this x8 minus 2x4 plus 1? This is also correct because this is nothing but
Fourth root
x4
of unity.
minus 1 square, which is, yes, x square minus 1 square, and then x square plus 1 square. So it has roots 1, 1, minus 1, iota, iota, minus iota, and minus iota. There are four repeated roots, and all are inside k, right? So it will be this. Clear?
Sir, first condition is minus 3. So minus 3 belongs to K.
But it is not the splitting field. The splitting field is the smallest field containing all the roots. Smallest field is q itself.
Okay, the reason for it. Okay, okay, okay.
Hmm. Now, 11th one is k, let k be the splitting field over q of the polynomial fx equal to x cube minus 3. What is the degree of the extension k q? So where does this contain all the roots of this polynomial? The solution is, so fx equal to x square minus 3 equal to 0 implies x is, sorry, x cube, or maybe I should write it in a better way. So, uh, so this is cube root of 3 and cube root of 3 uh, zeta 3 and cube root of 3 zeta 3 square. These three satisfies fx, right? And these are the only roots of fx. This implies k is uh, nothing but you adjoin q with these three, q root of 3, q root of 3, zeta 3, and that is cube root of 3 zeta 3 square. That is same as adjoining q with cube root of 3 and zeta 3, right? Now we want to compute the degree of this, and it is clear that k is an extension of q, uh, this this is an extension of q, so it satisfies. So from here to here the degree is 2 because zeta 3 is not inside q cube root of 3, and zeta 3 satisfies 1 plus x square over, so because it's a prime, so it satisfies 1 plus x plus so on to x raised to p minus 1. Here p is 3, so it will satisfy 1 plus x square over q, and hence it satisfies it over q uh, adjoined with q root of 3 as well. So the degree is 2 here, and from here to here the degree is
Degree
clearly,
2 into 3 यानी कि 6. Okay.
yeah, so the degree is 3 because clearly uh, this satisfies x cube minus 3 over q, and x cube minus 3 is also irreducible over q. Why? Can you tell me why it is
By
irreducible?
Einstein criteria.
Yes, over q by Einstein criteria. This time criteria. Okay, so this implies k over q has degree 2 into 3, that is 6. That is question number 11. Let's see question number 12. It says let k be the splitting field of field over q of the polynomial fx x cube minus 8. What is the degree of the extension k over q? Yes. Now can you tell me what will be the extent degree?
The polynomial irreducible polynomial x square plus 2x plus 4.
X square plus 2x plus 4. Means we are taking the splitting field. So first of all, what are the roots of this polynomial?
So first root is clearly 2,
Okay, roots of
and
fx are 2, then
the remaining in complex number
2 zeta 3 and 2 zeta 3 square.
3 square.
So but how to find these roots? So x cube minus 8 equal to 0 implies x is the cube root of 8, and Here you also have cube root of 1 you can put, right? This is 8 dot
Cube
1.
root of 23.
So this is 2 zeta 3 or 2 zeta 3 square. You vary these cube roots here. This is fixed, this is 2. When you vary from here, you will get these three roots. Okay. So uh, this implies uh, k is what? K is q adjoint with 2 zeta 3 and 2 zeta 3 square, and that is just q over zeta 3, and we know what is the degree of k over sorry, the degree of q zeta 3 over q we have seen a number of times, that is 2. It's zeta p has degree p minus 1. Okay, clear?
Okay, sir.
Question number 13.
Mm.
Hmm. It says K be the splitting field of over R of the polynomial x cube minus 3. What is the degree of K over R? So earlier we computed over Q in the 11th question, but now we are supposed to calculate it over R. So again, the same thing we will start with roots of fx are just you have cube root of 3, cube root of 3, zeta 3, cube root of 3, zeta 3 square. This implies k is r adjoint with these three. Now since this is a real number, right? Cube root of 3 is a real number. Therefore, k is just r adjoint with zeta 3. Okay. And zeta 3 is not inside R but satisfies 1 plus x square over R. This implies degree of k over, oh, sorry, degree of, yes, degree of k over R, that is that is same as degree of R zeta 3 over R is just 2. So in Q we have this degree to be 6, but here we just have degree to be 2 because cube root of 3 is inside R. Okay,
Sir, question is degree of extension over C, complex number.
1, because C is algebraically closed, so it will have all roots. It will have zeta 3 also, na?
Yeah.
So K will be what? C adjoint with zeta 3 and
Okay, okay. You are with question 13th. Okay, okay. I am asking for question 14th. Done, sir. They're complete.
So question number 14. So C is algebraically closed. Algebraically closed. Therefore, fx has all roots in C only, which implies K is just C, and thus the degree of K over C is just 1. Okay. Now the last question of this assignment. It says let fx and gx be arbitrary elements of qx of degree greater than equal to 1. Let k, l respectively denote their splitting fields over q. Which of the following must be true? So, uh, solution, let me just give it them some name: A, B, C, and D. So option A is not correct because it says that if two splitting fields have the same degree, then they are the splitting fields of the same polynomial. But which is not true, because you can consider, uh, for example, f equal to, you can take x square plus 1. It will have, and g you can take x square minus 2, right? So uh, they have the same splitting degree of the splitting field. For this, k is just or maybe here, k is equal to q adjoint with I, oh, and l is uh, q adjoint with root 2, and their degree is also same. K is equal to this, l is equal to this, and degree of k over q is same as degree of l over 2, because they satisfy the same degree polynomial and these polynomials are reducible. But you can see that the polynomials are not same. So the first one is not correct. The second one, kx equal to lx, then degree of f equal to degree of g. And that is also not true, because, for example, you can take f to be x square plus 1 and g to be just its power. It has same roots as f, just the repeated roots are there. So k will be in fact L, but and but degree of f is not same as degree of g, right? In fact, the fields are same. The degree will automatically be same, but still the degree of the polynomials are not same. C1, the C part says, so here the C and D we will tackle simultaneously. So C says fx is equal to uh, uh, gx hx for some hx in qx, then the degree of k over q is greater than equal to L over q, and the D part says that it is less than equal to L over q. So C is correct and D is not, because By definition, K is the splitting field of F. We say if Fx equal to Gx Hx and this capital K contains all the roots of uh, F, then it will definitely contains it will contain all roots of G and H as well, right? Because they are just F factors of F. So this will imply, so L was the splitting field of G, right? And K contains all the roots of G as well. And splitting field is the smallest field containing all the roots. So this implies L is a subfield of K, right? And which implies this is subfield L over Q is less than equal to K over Q, and that is what C portion says. L over Q is less than over equal to K over Q. And to neglect D, we should say that degree cannot be greater, right? Maybe I should use the same order as the question is saying. So K over Q is greater than equal to L over Q, right? But to neglect, because it might also happen now that it is always equal, and then D part will also be true. So to see that D is not true, we must give an example such that it is strictly greater. So the less than condition won't be there. To see that D is not true, uh, consider fx to be, say, x square minus 2 and x square minus 3. So this you can take as your gx, and this you can take as your hx. So uh, roots of fx are uh, plus minus root 2 plus minus root 3, right? But roots of, yeah, so yes, so this implies the splitting field of K is just you adjoint Q with root 2 and root 3, and that implies the degree of K over Q is 4. We have already seen that in one of the class we saw. We just take the tower that Q is contained in Q root 2, and then Q root 2 is contained in Q root 2 comma root 3,
Yes, certain.
right? So, and of course here L is just Q root 2 you take the roots of the splitting field of Gx, which makes it of degree 2. So it is actually less than this. So the D part is not true. So you have uh, only C to be the correct option. Okay. So with that, your assignment number 3 is done. I will just maybe say something about assignment number 4, and then we will stop. Maybe one or two question we can start. So So there is no problem in assignment number 3, I am assuming, right?
Yes, sir. Done.
Okay. Assignment number 4 is smaller. There are just 10 questions. We will see how much we can cover in the next 10 minutes, maybe. Then we will stop. The first question says, uh, let neta be the fifth root of unity. Choose all correct options. Q of neta is the splitting field of this. So, yes, wait, is it correct or not? So,
Sir, I have a little bit of confusing in statement 1 with statement 2. I know
explain.
1 plus I know x to the power 4, 3 is a irreducible polynomial.
See, this polynomial is same as x minus 1 uh,
Into that polynomial.
into this polynomial. This,
Yes.
right? So,
So can we
what
say
does
both are equivalent, sir?
yes, we just need to correct all the options, na? So this one, this root is already there inside Q. So only the roots of this polynomial are needed to be considered, because that is already inside Q. So why will you worry about it? You are adjoining the roots to Q, and if something is
Okay, okay.
already
Okay, fine, sir.
inside Q,
Right.
then there is nothing to be done, na? And this zeta, this neta generates all the roots. So it will generate one also, and in that way also you can see. This is a splitting field, and this is also the splitting field, right?
Okay,
Means
yes, sir. Fine.
Q neta is a splitting field for both. Q neta is a normal extension. So normal extension means it is the splitting field of a collection of polynomials, and also it is separable. So let me just tell the definition once. So normal extension means uh, any extension that is, oh sorry, I was confused with the yellow extension. So no, so it is the splitting, normal extension just means it is the splitting field of uh, certain collection of polynomials. So it is a splitting field of this x5 minus 1. So it is a normal extension as well. This is, since A is true, you can say just that, because it's a splitting field of some polynomial, so it will be the it will be a normal extension. Only the last part is not true, because this is not 5, this is 4. Okay, correct.
Okay, sir.
So let me just paste another problem. It says which of the following extensions k over f are normal. So normal again means it's a splitting field of some polynomial. So first one, is it true or not? So let me just give them some names: A, B, C, and then D. Then we will check it one by one. Solution number 1. So if it is a splitting field, then it must be the normal extension of, means it is a if it is a normal extension, and it should be a splitting field of some polynomial. And uh, so what is extra adjoining in this field apart from q? That is fourth root of 2. So we should see whether this gives you something. So fourth root of 2, this has minimal polynomial over q to be x4 minus 2, right? This is the minimum polynomial. It will satisfy it is satisfying this polynomial, and it is irreducible by Einstein criteria. So this is the minimal polynomial. And all so what are the roots of this polynomial? Roots of x4 minus 2 are just fourth root of unity times the uh, fourth root of 2. So that is 4 root 2 minus, sorry, minus fourth root of 2. Then you have fourth root of 2 times iota and fourth root of 2 times iota, and it's minus. So I should write like that, minus fourth root 2 iota, right? So, but these are not inside your k, right? If it is a splitting field of a polynomial, that is this polynomial, then it must be containing all roots of this polynomial, right? But it's not containing these two roots. So it is not a normal extension. But fourth root of 2 iota and fourth root of 2 iota minus iota are not inside uh, k. Thus, k is not a normal extension because k is not the uh, splitting field of this number. Because this is the only number that you want, you should keep in mind, because this is just q adjoining with some number. A normal extension means it's a splitting field, and splitting field is just q adjoined with certain numbers. You just check that whether this contains that number, uh, whether the minimal polynomial of that adjoint one has all the roots inside k. If it is so, then it's fine, otherwise no. Okay, so the b part, this is for a part. The b part is, now you need to consider this over q root 2. So now the minimal polynomial will change because your field has been enlarged. So this has minimal polynomial over q adjoint root 2 to be just x square minus root 2, because root 2 is inside this field. Earlier root 2 was not inside q, so we didn't consider this, but now the root 2 is inside this. And what are the roots of this? Roots of x square minus root 2 are 4 this and minus of fourth root of this, right? And they are inside this, and they belong to k. This implies k is a normal extension because it is a splitting field of this polynomial x square minus root 2 over q root 2. Okay, now this c part follows by a, right? C is k is a normal extension, follows by the explanation of part A. Right here we got that the four roots are these four, and if you adjoin q with fourth root of 2 and identity, then you have all the fourth roots, so it's a normal extension, right? Now uh, D part, C over R. So C over R is, so C is just R adjoint with I, and this is the splitting field of x square plus 1 over R. So this is also a normal extension. It is a normal extension. Is it okay?
Yes, sir.
So what shall we stop here? Maybe we can discuss
Sir, last question number third.
third also you want. Okay. Hmm. It says let F, K, and L be field extensions. Choose the correct options. If F containing K, K containing L are normal, then F containing L is also normal. So whether it satisfies the transitivity condition or not. So for uh, so here all three are not correct. First of all,
Sir,
this,
can we take the above example here?
which
Of
example?
example number two. Example number two, if you want.
Yes, 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 yes. You can take. You can take like
Is
that.
it possible or not?
Yes, yes. You take F to be Q, K to be just Q adjoint with
Root 2,
root 2, and L to be uh, Q adjoint with
fourth root of unit
fourth
2.
root of 2. So this follows from C part. Uh, what was the part? That was uh, B part, right? A and B. Just say the C question number 2. Okay. So this example will work. F over, so for K over, K is a normal extension of F, L is a normal extension of K, but L is not a normal extension of F. So this
First
also
is
implies
false.
uh, this also implies that C is false, because C is in fact a weaker version of it. That F contains K is normal, then F contains L is also normal. So in first we also have that K contains L to be normal, then still we were not able to see that whether F contains is no, L is normal. So C is just a special case of A. So if A is false, then C will definitely be false, right?
Yes, sir.
Only thing is now to see B. So B says that if F contain L is normal, means if the larger extension is normal, then the smaller one is also normal. So you take, for that also you can take the help of the previous example. So here you just take not the previous question I want to say. So F to be Q, take F to be Q, uh, K to be q root fourth root of 2 and L to be q fourth root of 2 comma iota. So here also I will say that C question number 2, because we have seen that. So here this is a normal extension, right? 4 root 2 I over q, right? And so you have taken this to be L and this to be F. So this is a normal extension, but part A says that this is not a normal extension. So all the three statements are false, thus none of the above will be there. Okay, so I think we can stop now. We will see the remaining questions of assignment 4, and we'll try to see some questions of assignment number 5 in the next lecture. That will be on 12 March from 6 to 8. Okay, any
Well,
doubts?
no, sir, clear today.
Okay, so
Thank you,
if
sir.
there,
Thank you.
okay, thank you, Vivek. So if there are no doubts, then I will stop here.
Sure, sir. Sir, can we? Hello,
Hello, yes, you were saying something?
sir. Can we
Yes,
set the lectures as we wish?
can we?
Set the next lectures.
See, this is going to be an announced lecture, so maybe some others might join. So the timing I can't change,
Okay, okay.
okay, because it's going to be announced by NPTEL team. So we will keep it as per the schedule. Okay,
Okay, sir.
okay. See you then in the next.
Bye,
Okay.
sir.